Math 265A, Cuesta College. I'm Joe Vasta. And we are covering 3.9, derivatives of logarithmic and exponential functions. So now we are going to deal with logarithms. So what's up with logarithms? We are to find the derivative of ln x. And so if you look at the PDF of this lecture, I'll include some of these properties here. So logarithms, the first three things on this sheet are definitions. Definition of a logarithm. All a logarithm is an exponent. A equals b to the c. Well, we can rearrange this equation, and logarithms were invented for this. So we can write c equals log base b of a. A and b are positive real numbers. So what we have here is just another form. Think of this equation and this equation are the same equation. This right here is Clark Kent. This right here is Superman. Log form. Okay. Definition. When the log appears not to have a base, it's really base 10. That's a common log. And when it says ln, like we have on our problem here, ln means that the base is e, and that's called a natural logarithm. Here are some properties of logs. Log base b of 1 is 0. Anytime the argument of the log, that's what that a is called, the argument. Anytime it is 1, then the log is 0. Anytime the base and the argument are the same, because you're really saying b to the 1 equals b, then it's 1. And then here's some other properties where log base b of b to the x is x, b raised to the log base b of x is x. Other properties that we will use. So make sure you become familiar with these again. Logarithms have the product rule, the quotient rule, and the power rule, just like derivatives have. So this is the product rule not for derivatives, but the product rule for logarithms. If you're taking the log of a product, it's the sum of those logs there. So hopefully you remember this from a pre-calculus class. You take the log of a quotient, it's the difference of those logs. And then you take the log of a power, that power can jump in front. And then we have the change of base rule, property 8, where you have log base b of n. You don't like that base b, you can change it to like another base, like base a, by going log base a of n over log base a of b. And these are the 8 properties of logarithms. You want to become familiar with them. We're not going to prove them in a pre-calculus class. We would go over where they came from. But now we must move on to calculus. The other thing you may have noticed on this sheet here is that we have something called derivation, and that's what I'm doing. I'm doing a derivation of this, a derivation of the derivative of ln x. Now some of you are like, oh, I hate those derivations because this is where you take out the quotient, the difference quotient, the difference quotient, and do the definition. I'm not going to do that on here. What I'm going to do is I'm going to go ahead and rewrite this so it says log y equals log base e of x. And this is just a different form. What I'm doing, I'm using the definition of logarithm. I'm changing it from Superman back to Clark Kent. So whenever I change logarithms, I always put an arrow. And this is going to be e raised to the y equals x. Okay? This is just from the definition of logarithms. Now what I'm going to do, because I'm trying to find the derivative, I'm trying to find y prime, I'm going to hit both sides of this equation with the derivative gun. So this probably reminds you of implicit differentiation. It is. If I hit anything with y, hit the derivative gun, hit y with the derivative gun, I'm going to put a little y prime. and then x is just going to be normal. So the derivative of e to the y, or e to something, is e to something. Doing a little chain rule here, and the derivative of y is 1. And then the derivative of y, because I did the derivative, it's going to be y prime. Okay. I really didn't need to put that one there, but I'll just keep it there to confuse other people who are looking at the PDFs. So I really should have just said e to the y times y prime. Now on the other side, the derivative of x with respect to x is 1. So what do I have here? I have e to the y prime equals 1. And I won't box the y prime here. So I'm trying to find out what y prime is. I'm going to divide both sides by e to the y. Y prime equals 1 over e to the y. So we'll move it up here. Now, look around. Where do you see e to the y? Because we would, if we could, like to have our derivative just have x's in it on the right-hand side. Well, e to the y is x. So I'm going to replace that e to the y with an x. So what does y prime equal? Y prime equals 1 over x. And so that is the derivative of the ln x. So let's go ahead and write out what we just found. The derivative of ln x equals 1 over x. Here's another one that you'll see in your book. The derivative of the ln absolute value x is still just 1 over x. Now this graph right here, y equals ln x, only lives on the right side of the y-axis. This one lives on the right side. It looks like that guy on the right side, and on the left side it's just reflected through the y-axis. And so it lives everywhere except x equals 0. And so the derivative is actually the same. You're going to see this one a lot, the top one and the bottom one. You may use it in the homework a few times, but you'll see that one a lot more. So let's go ahead and box that. Okay, so we have that right there. If some of you are like, well, where did you get this from? Well, I'll do this, but some of you might want to just skip ahead. Suppose y equals the ln of negative x. Okay, so I'm trying to show you that if there was a negative x in here, the slope would still be 1 over x. So this is still a derivation of this. So I'm going to go ahead and take the derivative of this using the chain rule. Y prime equals. Now I know the derivative of ln something is 1 over that something. So I'll go 1 over that something. And then I'll take the derivative of the something, which is negative 1. So what does y prime equal? It equals, the negatives cancel, 1 over x. So if there was a negative x in there, it would still give you a slope of 1 over x. And that's what this covers. This logarithm covers ln x and also ln negative x and puts them all in the same graph. So for those of you who didn't like this, that's all right. The important derivation is this one right here. And we used implicit differentiation to get us a nice formula for ln x. Now that we have this formula, it's something that you should probably try to memorize. We're going to go ahead and do some problems. So there's our first problem. And so this is the kinds of things you will get in your homework. We are supposed to find the derivative of the ln of that argument there that looks like a polynomial. So let's get to it. And I'm trying to get another piece of paper over here. Okay, so yeah, I have that. So what we want to do is we want to go y prime. Now, when I was doing the chain rule in the earlier lectures, I was actually taking out this pin and crossing out things, and it was great. But I was thinking back on that, and maybe when I crossed out things, when you're looking back at the PDF, it's harder to see. So what I'll do is I'll start crossing things out in this yellow here. Okay, so then that way you can see it a little easier on the PDF. So the big picture, the thing that's on the outside, the fence on this chain rule is the ln. I am asked to take the derivative of ln something. The derivative of ln something is 1 over the something. And that's the rule that we derived. The derivative of ln x is 1 over x. And then we're going to multiply. So I just got rid of the ln. So now we're not going to concentrate on that anymore. Now we're doing the chain rule, and now we have to take the derivative of the inside here. The derivative of this polynomial is 2x minus 3. And so our final answer for this, we have 2x minus 3 on the top. The bottom's not going to factor, so we'll just go ahead and write it as x squared minus 3x plus 5. And we used the chain rule. We also used the fact that the derivative of ln of something is 1 over something. So that's something you want to do in your homework. Let's go ahead and do another problem. Problem number 2. Okay, we have the ln of something. Okay, so this is another ln something problem, and that's all right. We want to practice this. This something is a little more complicated than the something on problem number 1. This something has a square root in which I am going to go ahead and write this square root as the 1/2 power. So that's what I'm going to do. So this is ln x squared plus x. This is to the 1/2 power. Okay, there's two ways to go about this. We're going to go do this the way that you'll see a lot of people do this. So here's the first way. You can tell me which way you like better. Taking the derivative of ln something, I don't know why I put the ln. So I might be having an off day. This might be a bad day for me to be making a video. The derivative of ln something is 1 over something. So let's write that. 1 over something. And guess what? That gets rid of the ln. Now I'm going to multiply this by the derivative of the something. Now the something, we have to do the chain rule as well. So now I'm going to redefine my something. So I'm looking at this right here, and I really have something to the 1/2 power. Well, something to the 1/2 power is 1/2 something to the, and you replace that by 1 less, so negative 1/2. So that takes care of the 1/2. And now I'm going to take the derivative of x squared plus x, which is 2x plus 1. Okay, let's simplify this answer. This x squared plus x to the negative 1/2 can cross the line, change the sign, So you have a 2 on the bottom. You have that guy right there. This guy crosses the line and changes the sign. Looks just like that guy, doesn't it? So there's the 2, and then we have a 2x plus 1 on the top. Okay, so we have 2x plus 1 on the top. And on the bottom we have 2 times, look, this thing to the 1/2 times this thing to the 1/2. Well, it's going to be this thing to the 1 power. We're not going to put the 1 power. And then we have 2 times x squared plus x. And sure, we can factor out an x, but it's not going to help reduce the fraction. So there's our derivative. Okay, let's go ahead and do this another way. So we're done with the problem, but I'm going to go ahead and write out our original function. It says ln x squared plus x to the 1/2, and I don't need those bigger parentheses. I'm going to use a property of logarithms, which is called the power rule of logarithms. It's property number 7. So you have a power, it can jump in front, and that's what's going to happen. So I'm not taking any derivatives, I'm just redoing this problem, and let me go ahead and put a line here. There we go. Whoa. Okay, so I'm just rewriting the function as 1/2 ln, we have x squared plus x. Let's go ahead and try out this problem now when we take the derivative. Y prime is. Okay, so I have 1/2, which is just a constant. I'm going to put it there, and then we have ln something. The derivative of ln something is 1 over the something, and that gets rid of the ln. Now we're just going to concentrate on the something, which is x squared plus x. So that's going to give me 2x plus 1. So it looks like we got the answer a lot quicker than the other way. The other way looked more complicated, but I wanted to show you both ways. Both ways give you the same answer, but maybe it pays to know your properties of logarithms. Because we knew the properties of logarithms, we eliminated doing the chain rule twice. We only had to do the chain rule once. We ended up getting the same exact answer. So that's what we did. Let's go ahead and do, if I can find a piece of paper, problem number 3. So we have these ones all on the same paper because I think hopefully we can become more efficient with this. We have y equals sine ln 2x. Okay, let's take the derivative. The thing that I see on the outside is the sine. Sine of something. The derivative of sine something is cosine something. Okay, I'll change it to this weird green color. Okay, so we get rid of the sine. We're using the chain rule, and now I'm taking the derivative of ln something. The derivative of ln something is 1 over the something, and that takes care of the ln. Now, what is the derivative of this 2x? Well, it is 2. And now we are done taking the derivative. We're just going to do some algebra cleanup. The 2's cancel. There's an x on the bottom, which stays on the bottom. And so this is the cosine of ln 2x all over x. So there's your answer. there's other ways of doing this. I mean, you could have said, I'm going to use the product rule for the logarithms and break that up into the sum of two logs. You'll end up getting the same answer. I think this way was the easiest way for this one. Let's go ahead and do problem number 4, and maybe now's the time when you want to start pausing the video and doing some of these problems on your own to see if you can get them. Okay, so what I have here is I have the product. So we have product, this one, there's the second part. And so when I do that, I'm going to use the product rule. Now my product rule says the derivative of the first times the second plus the first times the derivative of the second. And that is what I'm going to do. So y prime equals the derivative of the first, 2x, times the second, ln x, plus the first, x squared, times the derivative of the second. And the derivative of ln x is 1 over x. So there was no chain rule in this problem. So y prime is 2x ln x, that's that first part, and then x squared times 1 over x. One of the x's cancels, and you'll have plus x. So there it is. That's the answer to problem number 4. Let's go ahead and do problem 5. So once again, might be a good payoff for you if you can write this down on a piece of paper and see if you can crank out the derivative. It has a logarithm in it, has a quotient. Okay, so here we go. Y prime is. What I have here is I have the quotient rule. The top, the bottom. Okay, so we'll talk it out here. The derivative of the top, 1 over x, times the bottom, x, minus the top, ln x, times the derivative of the bottom, 1. This is all over the bottom squared. That is the quotient rule for derivatives. Let's clean this one up. 1 over x times x is 1. 1 minus ln x all over x squared. That gives us the answer. Let's go ahead and do another problem. This one right here. Y equals the ln of this. The argument is right there. It's one term. You could put parentheses around there if you'd like. So I'll do that in a different color because that might help you do this problem. There it is. So what I'm going to do is I'm going to go ahead and use the chain rule. I'm going to do the derivative of ln of something. So the derivative of ln something is 1 over something. Times. That takes care of the ln. Now within these parentheses, I'm going to go ahead and take the derivative of this, which looks like a quotient. Here's the top. Here's the bottom. The quotient rule says the derivative of the top, which is itself, times the bottom, minus the top times the derivative of the bottom, that's going to require some chain rule. The derivative of the bottom is 2 something to the 1. So 2 something to the 1. I'm not going to put to the 1. And then times the derivative of the inside, which is just 1. Now, could we have multiplied that out and did it that way? Sure, we could have. This is all over the bottom squared. What a mess this is. Now, what I have over here is I have 1 over 1, and I left room to do that. I'm going to do a copy dot flip on this. So this guy right here is going to be copy dot flip. And that's going to have the effect of just flipping that fraction. So watch this. You're going to look, it's going to look like this. X plus 1 squared over e to the x. Now this part looks pretty complicated. And I'm going to do a trick. So I'm going to go like this. I see that there are 2 terms on the top here. This guy and this guy. And each of those 2 terms has an x plus 1 in common. Now you can multiply it all out, then you'll just have a lot of factoring to do. They also have an e to the x in common. So on the top of that fraction, I'm going to factor out an e to the x, x plus 1. So the thing that is making us suffer a little is the algebra. And so when I factor it out of here, I just have an x plus 1 left. And then I have the minus sign. Minus what? Well, this is going to be minus 2, because the orange part got factored out. So minus 2. This is all over x plus 1 squared is to the 4th. So what I have on the top is I have an x plus 1 squared here and an x plus 1. That gives me an x plus 1 cubed. I have an e to the x. And then inside these brackets I have an x minus 1, which I'll just write as x minus 1 in parentheses. And on the bottom I have an e to the x, which is that guy right there. And then x plus 1 to the 4th. Now things can cancel and things will cancel. The e to the x's cancel. And then these guys, there's 3 of them up there and 4 of them down there, so you're going to get some reducing like that. When it is all done, you end up getting x minus 1 over x plus 1. That is the answer. That completes problem 6. Now, looking back at our problems, I remember there was one where, I think it was problem 2, where we used properties of logs when we did the second part, and it made the problem easier. And so that's actually what I want to do on this problem. We should still get the same answer, but what would happen if I actually used the quotient rule of logarithms? So I'm going to do this problem again, and I know some of you are like, well, what a waste of time. But I mean, math is a waste of time, so why are you so surprised? I'm going to do 6 again, and what I'm going to use on 6 is the quotient rule of logs. See, I have log of something over something. I'm going to break it up into subtraction. And then I think I'll use the power rule as well, because I see a power right there. Let's go ahead and see what we have from this. Say that this is going to be ln e to to the x minus ln x plus 1 squared. Okay, now this guy right here, this is log base e of e to the x. Log base e of e to the x. That's exactly what we have here, log base e of e to the x. I know this has b's in it, so this is all going to go away. Sometimes I call this the popping log property, because that log base e of e pops, and then you just have an x. So let me color code this for those of you who are like, what just happened? This guy right here, from properties of logs, becomes an x. I know I can make the x jump in front of the log, so it's x times ln e, and ln e, e raised to what power gives me e, that just becomes 1 then, and so you just get x, either way you do it. So that came from there. Okay, so that was one of the properties, and then we have the power rule for logarithms where the 2 can jump down front. So I have minus 2 ln x plus 1. Okay, let's go ahead. This is still y equals, I have not taken the derivative, and now I'm going to take the derivative. Y prime equals, the derivative of x is 1. The derivative of this, minus 2, is going to go out here, and then we have ln of something. The derivative of ln something is 1 over that something. So now I'm doing some chain rule here, and that gets rid of the 2 ln. And now I'm going to do the derivative of the something, which is 1. So my final answer looks like this. It looks like 1 minus 2 over x plus 1, which is an acceptable answer. And you might think to yourself, well, Joe, that is not what we got there. We got x minus 1 over x plus 1. So I'm going to now do some algebra on this to show you that it is the same answer. So I'll do that in blue, but we're done with this problem. All I'm going to do is get a common denominator, and that common denominator is x plus 1. So I can write 1 as x plus 1 over x plus 1. And so this gives me x plus 1 on the top, minus 2, all over x plus 1. And then on the top you have x plus 1 minus 2, which is x minus 1. And on the bottom it still says x plus 1. So this is just another way of writing your answer, which is the answer that we got when we did it the longer way. So yeah, there were some properties of logs that we used. We simplified the function, and then the derivative wasn't as traumatic. Look at the derivative here. We had to do the chain rule and the quotient rule all within here, and lots of algebra. On this one we had properties of logs that simplified it, and really all we had to do was a chain rule, just a little tiny chain rule as well. So that was problem number 6. Let's go ahead and do problem number 7. Hopefully, we've learned our lesson. Maybe if we could use properties of logarithms to sometimes clean these up, the derivative is not going to be as traumatic. So let's go ahead and do that. So I'm writing the same function again. I'm going to write this as ln, and the first thing I'm going to do is take that square root and make it 1/2 power. Okay, the next thing I'm going to do is I have a power, the ln of something to a power, the power is going to jump in front of the ln. So this gives me 1/2 ln x cubed cosine squared x. Now what I'm going to use is the product rule for logarithms, ln of that product. So this is 1/2, and I'm actually going to write this incorrectly. I'm going to see if you can catch what I did wrong. So the product rule says ln x cubed plus ln the cosine squared x. And I'll put parentheses around these arguments, even though you don't need that for those arguments. And so I'm going to ask you, what did I do wrong here? Of course, I can't hear your answer because this is a video, but what I did wrong was I replaced this with this. This whole thing is multiplied by 1/2, so you must have parentheses. Now this guy right here, this cosine, I'll do this in purple. It's a cosine squared, which means it's really cosine x. This whole thing is squared. The reason I'm telling you that is now we have something to a power. We can use the power rule for logarithms and make that 2 jump in front of the ln. And same with the 3, we can make that jump in front of the ln, so that's what we're going to do now. So this equals 1/2, we'll just keep that out there for now, 3 ln x then we have plus, and then the 2 can jump out front, 2 ln, and I'll put parentheses around this cosine because it does look a little weird without them, ln cosine x. Let's go ahead and write this one more time. I'll distribute the 1/2 through, so I have 3 halves, 3 times 1/2, ln x plus what? The 2 times the 1/2 is 1, so this is just going to be plus ln cosine x. Woo! We have not done any calculus. All we've been doing is properties of logs. And you may have remembered problems in your pre-calculus class where they give you something and they say expand the log. And that's what we did. Now, where's the usefulness of this with problems that I'm about to do? It's easier to zap this with your derivative gun than it is to zap that with your derivative gun. Okay, so now take out your derivative gum. Well, that would be cool if there was some derivative gum. And we're going to go ahead and take the derivative of ln x, which is 1 over x, but there's a coefficient there, so this is 3 halves times 1 over x plus a little bit of a chain rule here. So ln something. What is the derivative of ln something? It is 1 over something. That takes care of the ln. And now we're going to take the derivative of the cosine, which is negative sine. So what we have is we have 3 over 2x, and then there's a minus. Do you remember what the sine over the cosine is? The sine over the cosine happens to be the tangent. So there's your derivative. And I dare you to do this problem without the properties of logs. You know, maybe you would start here. And I guarantee you, when all the dust was settled, you can get to that answer. Now some of you are like, nope, I'm going to use the properties of logs, and that's good. So let's go ahead and do the next kind of problem. So let's do problem number 8. Problem 8, we have y equals x raised to the sine x. What we're going to show you now is something called logarithmic differentiation. Okay. Let's go ahead and do this. How do we do this? Because now we have variables within the base, and we have variables within the power. What we're going to do is we are going to ln both sides of this equation. Okay, so I'm going to say ln left-hand side equals ln right-hand side. Now, almost looks like I made this problem worse. But there was nothing else that I could do. I mean, I'm not going to use the power rule and replace this with sine x minus 1, because the power rule only works when the exponent is a real number. So there's no way I could do that. So when I do this, look what this is on the right-hand side. We have the ln of something to a power. I'm going to use the power rule of logarithms and make the sign jump in the front. So I have ln y equals, the sign jumps in the front, I'll put parentheses around it, sine x times the ln x. So what I'm going to do next is I'm going to go ahead and hit both sides of this equation with the derivative gun. dx. And it might remind you of implicit differentiation. I'm going to take the derivative of ln something, which is 1 over something. And because this is a y, I'm going to put a little marker by it, this y prime. And I'm not going to box it this time because I'm only going to have one of them, and it's always going to be on the left-hand side. Now on the right-hand side, I'm going to go ahead and do the product rule. The product rule, I have a product of two things, this guy and this guy. So I'll talk through it right now. The derivative of the first, which is the cosine, times the second, ln x, plus the first, sine x, times the derivative of the second. The derivative of ln x is 1 over x. And so that's what we have there. I've got to mute the computer because it's making little noises. Okay, so there we are. So what I have here is, I mean, there's the answer on the right-hand side, but what am I trying to solve for? I'm trying to solve for y prime. And y prime is right there. The way to get our answer is to multiply both sides by y. Because those y's cancel, and then I'll have y prime equals y times the right-hand side. So y times this, cosine x ln x plus sine x over x. Now I still don't want my derivative to have a y in it, and so what I'm going to do is realize that y equals x raised to the sine x, and I'm going to replace that with that. So my final answer then is going to be x raised to the sine x. So that's what that y is. And then over here we have the cosine of x. And I put the parentheses around that so it doesn't look like I'm taking the cosine of x ln x. That's why I put the parentheses around the cosine x. I have x ln x there, and then plus sine x over x. And there we have our first example of logarithmic differentiation, where you ln both sides of the equation to simplify. So to simplify the right-hand side so we can actually take the derivative. Now, this function here, it has a form called g to the h. Your book is going to call those guys, you know, when you have a variable in the base and a variable in the exponent, your book's going to call them tower functions. It's just the word they use. So in your book, they may give you another method. I don't want to overload you with methods. I think this method is the most efficient because it's going to work for more general things besides tower functions. So this is logarithmic differentiation. I just wanted to kind of warn you. I mean, this is what your book calls them. Tower functions. So now we're going to go ahead and do another problem where we're going to use logarithmic differentiation. So here it is. So logarithmic differentiation. I'm too lazy to write it all out again like I did on the first page. So you might want to try to do this on your own. However, you only saw one, so if you're still like, I don't know if I want to do that, then don't. Logarithmic differentiation says take the natural log on both sides of the equation and see what we get. Now, it looks like we're making more of a mess. Well, let's just do it anyway. So this is the ln of y equals the ln of this junk, the right-hand side. So this is x to the 7th tangent 6th. And then this is all over e to the 5x. Now, is it true that I could have just taken the derivative of the right-hand side? Yeah. But it's going to be a quotient rule mixed with product rule, mixed with chain rule on the bottom. It's going to be a mess of algebra. So we're just taking this approach because we know that logarithms, properties of logarithms, can really help with quotients and products. And that's the whole idea. So what I'm going to be doing, a lot of the steps that come after this are not even calculus steps. So let's continue. This is ln y equals, the quotient rule for logarithms says this, ln x to the 7th tangent to the 6th. And I'll go ahead and keep the parentheses around that. And then we have minus ln e raised to the 5x power. Okay, let's take a look at that e raised to the 5x power. This guy right here. The ln of that. Now, going back to the properties of logarithms, this is that popping property where you have log base e of e to the 5x. This one right here. Log base e of e to the 5x this time. And so that ln, the log base e of e, that's going to go pop, and this is going to give you just a 5x. Meanwhile, over here, we're going to use the product rule of logarithms. So I have ln y equals ln x to the 7th plus ln tangent to the 6th minus 5x. Now, this tangent to the sixth is really tangent x, the whole thing raised to the sixth power. So we've seen this before in this lecture. The 6 is going to jump in front of the log, so this is the power rule for logarithms, and the 7 is going to jump in front of that log. So let's write that down. This is ln y equals x ln x, and then over here plus 6 ln tangent x. Whenever we have a trig function as the argument of a logarithm, I just find it good taste to put parentheses around that, because otherwise it messes with my eyes. So the 6 goes out front, and then we have minus 5x. Okay, so it is now time to take out your derivative gun and zap both sides of this equation with the derivative gun. So d dx. That's what we're going to do here. So the derivative of ln y, so the derivative of ln something is 1 over that something. And then because we took the derivative with respect to y, we have a y prime equals. Now that looks very familiar because that's exactly what happened in the last problem. 1 over y times y prime. And so when you do logarithmic differentiation, that's always going to be the same thing. Now the right-hand side is going to be different. I'm taking the derivative of 7 ln x. So the derivative of ln x is 1 over x. So this part becomes 7 over x. This one's going to be the tough one right here. So this is 6 times the ln of something. So the derivative of 6 times the ln of something, I'm going to put the plus 6. Derivative of ln something is 1 over the something. So I'll go 6 times 1 over that something. Doing a little chain rule here, so those guys we can kind of disregard. And now I have to do the derivative of the tangent x. The derivative of tangent x is secant squared. So that takes care of this whole term right here. We just did a little chain rule. And now the derivative of negative 5x is minus 5. So the rest of this problem is just cleaning things up. And mostly just cleaning up, well, it's cleaning things up, but it's also dealing with this 1 over y. So we'll do both things at the same time. What should I do first? I think I will do this mess over here. 1 over tangent. 1 over tangent is sine over cosine. So I'm going to go s over c. I want to see if this trig cleans up. And since I'm changing everything to sines and cosines, this is acceptable for me. The secant squared, well, the secant is 1 over cosine, so this secant squared is going to be 1 over cosine squared. This guy right here is 1 over 1 on the top. Copy dot flip will give it cosine over sine. And then over here we have 1 over cosine squared. A cosine down here cancels with the cosine upstairs, and you end up getting 1 over sine cosine. Well, we'll write it alphabetically, cosine sine. And so that's what we want to replace this with. It was able to be reduced because we actually were able to reduce that with that. And this is actually a little simpler. We'll move this off. The rest of this problem really is just doing some algebra and multiplying both sides by y. So that's what I'm going to do. I'm going to multiply both sides of this equation by y, I end up getting y prime equals y times 7 over x, don't have to do anything with that, plus 6 times this blue part, so this is really 6 over, and we do want to write out the cosine and the sine now. Cosine x, sine x. We have minus 5. Okay. So we don't want to leave this as our answer because we have a y there. We'd like to somehow get rid of that y. Well, we know this right here. Here's y right here equals this expression, our original problem. So that's what I'm going to do. I'm going to put an x to the 7th, tangent to the 6th, e to the 5x on the bottom. So here it goes. So y prime equals x to the 7th, tangent to the 6th, and this is all over e to the 5x. And then, of course, this is multiplied by what I see in those brackets. I could have put big parentheses as well, but I decided to go with the brackets. 7 over x plus 6 over sine x, or cosine x sine x. There. Oh, come on, white out. This whiteout experience debacle brought to you by Staples, so make sure you get those ones because that's the kind of job it does. We have cosine x sine x. I should really get the liquid whiteout because that would make this fun, and then I'm writing on it and it's smearing, and then people are like, wow, these lectures just got exciting because, you know, he got whiteout all over his hands. Ha 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 ha. I mean, that's how boring these lectures are. So maybe I'll bring some white out and like dump it or something. Maybe an ink well, and then like ink dumps out. That would be great. These are dreams I have that they'll probably never come true. So let's get back to this. Minus 5. And so, you know, I'm sure the book would probably say, hey, let's do that double angle identity and, you know, mess with your minds and write a different answer in the back that just used a weird trig identity, but we're just going to leave it like this. So there's the answer to problem number 9. We used logarithmic differentiation, where we ln both sides. You know, of course, this always happens on the left-hand side when you do that, but then you multiply by y, and yes, it does look bad, but it would have been worse, maybe it would have been worse, to do this problem directly, because on this one, unlike problem 8, where it was the tower function, this one we could have done directly. So I'm not going to challenge you to do that directly using the quotient rule and all that, but if you had enough perseverance, you should be able to get to this answer. It would be painful algebraically. Let's go ahead and do our next problem. Well, before we get to number 10, we're going to go ahead and do a derivation. So here's derivation. What is this going to be? Well, we're going to derive a formula for 2 to the x. And so let's get something straight. We know that if our function was e to the x, that the derivative is also e to the x. So you might think, oh, well, the derivative of this is going to be 2 to the x. No, 2 does not have that special property. See, e is such a special constant that it's the only function where you take the derivative and it's itself. So this, we don't know. We've never done this before. So how am I going to do this problem? And it's not a numbered problem because it's a derivation. So we'll finish this problem and then we'll go, oh, there must be a pattern, and then we'll write out a formula for that. So I don't know what to do. How would you approach this? Well, what we're going to do is we're going to ln both sides of this equation. Ln of y equals ln 2 to the x. So we're using a little logarithmic differentiation. And the reason I did that is now I can see this x can jump out front from the power rule of logarithms. So that's what I'm going to do next. ln y equals x ln 2. Okay, now it's time to take the derivative on both sides. So that's what I'm going to do. We're going to dx both sides. On the left-hand side, the derivative of ln y. Well, I go the derivative of ln something is 1 over that something. And then because I took the derivative with respect to x of something with a y, I'm going to put a little marker here, y prime. This equals, so you might be thinking to yourself, I'm going to do the product rule here. Well, ln 2 is just a constant. It's like taking the derivative of like 7x. The derivative of 7x is 7. Well, the derivative of ln 2x is just going to be ln 2. Okay, so the next thing I'm going to do, I'm trying to solve for y prime, is multiply both sides by y. So I end up getting y prime equals y ln 2. Now the y can get replaced with what? 2 to the x. So y prime equals 2 to the x ln, and we don't need those parentheses anymore, ln 2. And there's the answer. So what if this had said 3 to the x? What would the derivative be without going through this mess if you just were looking at this? It would say 3 to the x, ln 3. I hate to do this again to you guys, but what if it had said 13 to the x? Well, then the answer would be 13 to the x, ln 13. So, if you have to take the derivative of b to the x, we just kind of derive this using a 2 instead of a b. Then it's going to be b to the x ln b. So that's the big formula. We should take out the Sharpie pen. Oh, and I smeared the b. Great. Now it looks like I didn't smear it. There's the formula. Now, the funny part is we've always used this formula when we did this, without actually knowing it. So watch this, and I'll do it like maybe in red. When you take the derivative of e to the x, we know the answer, it's e to the x, but let's use this formula. It is e to the x ln e. And ln e is log base e of e. E to what power gives you e, or you can look at property 2. Ln e, however you want to describe it, it's always going to be 1. And it's not however you want to describe it. I don't know why I said that. So the answer is e to the x times 1, which is e to the x. All the other times, you know, when the base is something else besides e, then you're going to have ln of that base, which is not going to just become 1. The only time it is 1 is when it's ln e. So yes, this even applies to e to the x, and we see it applied there. And so this is our new formula that we have. Let's go ahead and do problem number 10. And find problem number 10. Here's problem number 10. Okay, so find the derivative. I mean, that's what a is. So that, and then I put this in because in your homework you get a few problems where they ask you to evaluate the derivative at, and they like to say a equals 0. So we'll do that after we do this first part. Okay, this first part, y prime, is, looks like what we have here is the chain rule. You could put parentheses around the exponent, and we're really going to say, do we remember, now it was on the last page, and it's not in this video right now, it's not in this part of the video. Do you remember the derivative of 10 to something? And this is when you go, oh yeah, I do. The derivative of 10 to something is 10 to something times, and I'll put this in parentheses, ln 10. Okay, so that is the derivative of 10 to something. Okay. We get rid of that because we're doing the chain rule. And now what we're going to do is we're going to do the derivative of this right here. It's the derivative of 3x plus 7. It is just 3. Now, we like to put our coefficients in front, so we're going to put the 3 in front. And then I'll put the ln 10. I'll keep it in parentheses. I'm feeling a little insecure, so I might as well do that. Now, a lot of people would say, hey, Joe, let's go ahead and go 3 times 10. Well, we can't do that because of the order of operations. Order of operations says this exponent it's done first before the multiplication. So Aunt Sally, she'd be slapping you. She even saw that you wrote this as 30 raised to that power, because that is not what we can do. Let me give you an example of how that would be wrong. How about 3 times 2 squared? Okay, so we know that this is 3 times 4, which gives us 12. But if you're like, yeah, I hate Aunt Sally, and then you're like, let's just do multiplication first, you'd get 6 squared. You'd get 36, which is not 12, by the way. So we don't want to do that. Okay, and we don't want to go 3 times 10 and write that as 30 raised to that, because then we're breaking the rules of our orders or order of operations. So let's go ahead and box this answer. And part B says evaluate the derivative at a equals 0. So that just means put x equals 0. That's what they mean by that. And so let's do this. Y prime of 0 is 3 times, I'm plugging it in up here to this function, 10 raised to the 0 plus 7, raised to the 7 power, and then this is times ln 10. And then we can write this as, this guy right here I think is going to be 10 million. It's a 1 with 7 zeros after that, so multiply that by 3, it's going to be, so you first do that, and then we multiply that by 3, so it's going to be a 3 with 7 zeros. 1, 2, 3, 4, 5, 6, 7 times the ln of 10. And that gives you some slope at 0. And if you were really bad, you could say, hey, let's do the power rule of logs and make that become the exponent. Let's not do that. Here's our answer. And so that is what we have there. That gives us what we want. 30 million times the ln of 10. So I think what we should do now is another derivation. So there it is. So we know how to take the derivative of b raised to the x. And we know that the derivative of ln x is 1 over x. Okay, so let me go ahead and talk about what we know. We know that the derivative of e to the x is e to the x. And then we just generalized that right now, and we said, oh, guess what? The derivative of b to the x, with any legal base there, is b to the x ln b, where this guy right here fits into this mold. So this is more specific, this is more powerful because it describes the e to the x, but it describes all of them like 10 to the x. Okay. We also know the derivative of the ln x is 1 over x. That's great. But we've never considered yet the derivative of any base on the logarithm, log base b of x. We've never done that. We don't know what that is, and at the end, hopefully we can write out the formula there. So in this case, we have a 2 here. After we get the answer, we'll try to extrapolate. We'll see the pattern and put the answer there. So how am I going to do this problem? If you want to ln both sides, that's legal, but it's going to be quite messy on the right-hand side. So we are not going to do logarithmic differentiation. What I am going to do, I'll put an arrow here. But we're not going to do logarithmic differentiation yet. The arrow means I am changing from Superman, that's log form, to Clark Kent, that's exponential form. So I'm just using the definition of a logarithm, and I'm going to rewrite this. I always start off with the base, so the base is 2, the exponent is y. This equals the argument, which is x. Okay, so that's what I have. Now I'm going to hit both sides with the derivative gun. So we'll do some implicit differentiation here. So we're not doing logarithmic differentiation because I'm not ln'ing both sides. I am doing implicit differentiation. Now here we go. The derivative of the left-hand side, the derivative of 2 to the y. Well, we consider the derivative of 2 to something, which falls right here. So this is going to be 2 to something times the ln of 2. And we'll write that like that. Now, because I took the derivative of something that had a y, I'm going to put a little marker right here, y prime. I'll box it this time. Now, the right-hand side is going to be the derivative of x. That's pretty simple. It's 1. So now I'm going to go ahead and solve for y prime by dividing both sides by 2 to the y ln 2. So I have 1 over 2 to the y ln 2. Now I don't like my derivative to have y's on the right-hand side. So is there a way that I could replace the 2 to the y with anything with x's? And the answer is yes. I can replace that 2 to the y with x. And when I do that, I get y prime equals 1 over x ln 2. And that's the answer. So suppose there was a 3 there instead of a log base 2, log base 3. How would that change this answer? Everything would be the same except there would be a 3 there. And if there was a log base 13, everything would be the same except this would say ln 13. So our answer, let's fill this in because we've now finished this, happens to be 1 over x times the ln b. So there's an extra factor of ln b on the bottom, just like there was an extra factor of ln b on the top for this guy. A few things we want to mention before we move on here. And the first thing would be that this guy, derivative of ln x, fits into this mold. So I'm going to show you how that's done. d dx ln x. So now, normally we would say, oh, the derivative is 1 over x. But let's put it into this mold here. And when we do that, and we kind of did that when we were looking at the b to the x formula for the first time. So when I put it into this mold, I get 1 over x times the ln of the base. And what is the base up here? The base is e. And do you remember what ln of e is? ln of e is 1, which gives you 1 over x. So this guy does fit in this mold. Now we used the derivative of ln to actually do this derivation here, so I'm not saying that we didn't use this. We used this to derive this, but I'm just saying that this guy does fit into the mold, and we just showed that right there. So with a thick pen, this is actually a good part right here, we have those formulas that we've covered in this section where actually we already knew the e to the x one, and then these are the new ones where we knew e to the x, and then we first did ln x, and then b to the x, and then log base b to the x. Now this formula is similar to the other formula as well. Remember when I had ln absolute value of x? So if I have to take the derivative of the log base b absolute value x, it's simply going to be the same thing, 1 over x ln b. I'm not going to prove that, but you can throw a negative x in there and do a little chain rule using this formula, and you can find that for the negative x, it gives you the same thing. Okay, so there's our derivation. These are the formulas that you'll be using. It's best to know the formulas. It's always best to memorize the formulas, because when you hit your next technical class, they're going to expect that. The ones that come up the most are the first one and the third one. Okay? But when these ones come up and you forgot them, and most of the time people forget them, and they're like, oh, what was that? Where was that extra ln? And then you look it up or you figure it out. So problem number 11 gives us a little practice on what we just did. Okay? You'll get some like this in your homework. And so problem number 11 says, find the derivative of log base 8 of x squared plus 1. So how do we do this? What I'm going to do is I'm going to use the chain rule. So y prime equals, okay, log base 8 of something. So you can look back on the last page. To take the derivative of log base 8 of something, it's going to be 1 over, now it used to be x, but now it's the something. So this is the something. So this is x squared plus 1, and then times the ln of 8. Times. Now, some of you might be going, whoa, what just happened? We just did this formula right here. And instead of having an x there, we had this junk. So this junk would, right down here, would get replaced with that junk right there. So that's what we did. Okay, this is multiplied by, I'm doing the chain rule, I just went ahead and got rid of that. The derivative of x squared plus 1, which is 2x. So my final answer, I don't think there's anything really that I can do, is write this as 2x all over x squared plus 1. And we have the ln 8. There's my final answer. Okay, well, there is another way of doing this problem. So let me get the ruler out. I'll draw a line down here. And the other way of doing this problem is the following. This way here is probably the best way. Okay, so I have log base 8 x squared plus 1. Okay. What I could do, I can find the property, is use property 8, which is the change of base rule for logarithms. And I'm going to change the base of this log to base e, which means ln. So that's what I'm going to do. So I'm going to write this as ln x squared plus 1 divided by ln 8. So what I'm going to do is I'm going to pull out that ln 8 and put it out front. So 1 over ln 8 is out front, and then this is multiplied by ln x squared plus 1. This right here, 1 over ln 8, is just a constant. So now let's go ahead and take the derivative. The derivative of constant times something, I'm going to write out the constant. And now I still have to do the chain rule, but now it's the ln of something. The derivative of ln of something is 1 over something. That gets rid of the ln. And now we do the derivative of the something, which is 2x. And look what we have. I mean, when we put it all nicely together, we get 2x on the top, and on the bottom, I'll put it in the same order if we have it over here. We have x squared plus 1 in parentheses times the ln 8. And so this gives us the same answer. So you can change your base always to base e, and then do the problems this way. Or we can just take advantage of those formulas that we have for log base a, or was it log base b? I think it was log base b, and then go ahead and get it done a little bit more efficiently. So that concludes problem number 11. We're going to go ahead and move on. We're almost done with this section. If you're thinking, man, I hate logarithms, well, you have to get used to them a little more. We're going to do a derivation, and then we'll do problem number 12. Okay? So now we can do this derivation. And you're probably thinking to yourself, well, Joe, we already know what the answer is. We know this is going to be r times x raised to the power r minus 1. And that's correct. That's what we're going to derive. But our proofs of this power rule, we first did it for natural numbers, and then we did it for integers. Okay? But we've never done this power rule, proved this power rule for any real number. And that's what we're going to do right now. So, I mean, this real number here could be pi, or it could be square root of 3. And so we know the power rule, but we've never seen the official proof. So some of you are like, yeah, I'm just going to skip over to problem 12. You're not going to hurt my feelings, because I'll never know. Okay, so here goes the proof. I want to take the derivative of this, and suppose that is like a pi up there, r equals pi or whatever, and I was like, well, I've never derived that, so I'm going to ln both sides. So what I'm doing is logarithmic differentiation. I'm going to go ahead and take that r and jump it in front of the ln using the power rule of logarithms. So I have ln y equals r times the ln of x. Now I'm going to hit both sides with the derivative gun. d dx. The derivative of ln y, well, ln something is 1 over the something. And then because we took the derivative with respect to x on a y, we have to put a little marker here, y prime. Meanwhile, on the other side, the derivative of constant times ln x is going to be constant times 1 over x. I'm going to multiply both sides of this equation by y because I'm solving for y prime, so I have y prime equals. Well, this is going to be, I'll write it as r times y. R times y all over x. And we want to figure out what we can replace this y with. Well, we have that right up here. So this equals r x to the r all over x. And we can use properties of exponents to write this as r x to the r minus 1. Now in the future, let's not do all this. Let's just remember our power rule. So for instance, if y is x to the pi, then y prime is, we'd put the pi here, times x to the pi minus 1. Okay, so there's a little problem that we can do. And we knew about this. We knew it was true for all real numbers. I may have even said it was true for all real numbers, but now we've got the legitimate proof which uses logarithmic differentiation, which is very powerful. It's a very powerful tool. So now we are coming to the end here. We have one more problem to do. This is problem number 12. So in your homework, they'll ask you to take the second derivative. That's what that really means, d2, dx2. It says take two derivatives of this. If you do not like this notation, you know, you're doing your homework, you're like, oh, yuck. Then this is what you do. You say, okay, let's just go ahead and write this as y equals ln x squared plus x, and we'll just find y double prime. Okay, so, you know, if that makes you feel uncomfortable, it's just saying two derivatives. We can do it this way. Okay, so, once again, to remind you what this says, this is really saying d dx of this right here. That is really the notation for that. And so you're taking the derivative of this, and then you're taking the derivative of that result, which is the second derivative. So let's go ahead and do this, and you might want to pause the video and see if you can find the second derivative on your own and simplify it. Okay, so derivative of ln of something is 1 over that something. Doing a little chain rule here. So we get rid of that ln. And then we take the derivative of the something. The derivative of the something is 2x plus 1. So it looks like my first derivative is 2x plus 1 all over x squared plus x. Now, I can factor an x out of the bottom, but that's not going to help me simplify the fraction, though. The fraction is already simplified. We want the second derivative, so now we have to go and move on. Now, this is not going to require logarithms at all. We're just doing a basic quotient rule of derivatives. Okay, so I'll keep to the pattern that I've been doing. There's the top. There's the bottom. The quotient rule says the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. rest of this problem is algebra. So I'm going to go ahead and do lots of algebra here. Distribute the 2. 2x squared plus 2x. This is what I'm going to do. I'm going to FOIL and distribute the negative at the same time. This is a very dangerous thing to do if you are tired or drunk. So please do not do that in those situations. So I have, now watch, I'm going to mess it up, minus 4x squared minus 4x minus 1. This is all over this guy right here. X squared plus x, 1 of these squared. Okay, let's combine like terms. I end up having negative 2x squared and then minus 2x and then minus 1. This is all over x squared plus x, 1 of these squared. Now you might think, could this fraction be reduced? And that's actually a legitimate concern. Over here, I'm just going to see what the top factors into. Now that's a trinomial. I'm going to factor a negative 1 out of that trinomial. Factors of 2 that add up and give you 2. That's not going to happen. So this guy does not factor over the rational numbers. So we really didn't have anything to worry about. This is our answer. And I better write does not factor. And usually most teachers will say that, does not factor. But I'm going to say over rationals. Because it does factor over the complex numbers. Now if you're thinking, what did you just say? Forget what I just said on that. There is the second derivative. And this completes 3.9. So do your homework. Have a good day. I'll see you in the next video.